Hey kiddos, here's your review for Spiral 14. Here we got one multiple choice section that's going to be based on area and volume. Just like last time, you got to set up the integral and then you can use a calculator to solve these things. And for our first one, we're looking at 2 to the 0.25 x plus 1 and 3 secant of x minus 3, which by the way on your calculator you're going to have to write as 3 times 1 divided by cosine of x, and then minus 3 in order to get that to show up, because there's no secant button on your calculator. Okay, I'm going to graph these things, press pause while I do that, and then see where these intersections are. Okay, looking at my graph, on my calculator, we've got an exponential function. That's that first part, which looks something like this. And then we've got secant, which looks like a whole bunch of u's. Specifically, the one that I'm going to use is the one around the y-axis. So we're talking about something that looks like this. That means I've got to find 2 points of intersection, and I'm going to use my calculator to do that. I'm going to go to second calc, intersect. I've got to hit enter a couple times to choose the two curves, and then I'm going to find the point of intersection by getting close to it and pressing enter again. The first one is at it's negative 0.9046. I'm going to make my y value down below, comma 1.85. Actually, I don't even need that. I'm just going to find the 2x values, so that's cool. I'm going to do the same thing, second calc, and go to intersect. Select my two curves, and when I press enter, we get 0.9530 or 9531. Okay, so we're going from, all right, and that integral is going to be from negative 0.9046 to positive 0.9530, and that's going to be 2 to the 0.25 x plus 1 minus 3 secant of x minus 3 dx. I need to see the setup for you to get credit for this. It's not enough just to get an answer. You have to show what that is. So then when I go to fn int, and again that's negative 0.9046 to 0.9530, 2 to the 0.25x, and then plus 1, and then minus, and again I've got to do this as 3 times 1 divided by cosine of x, and then minus 3. I put that in parentheses, and then dx. I'm going to press enter. It might take a second. I get 2.6932. If you're in the AP side of this course, you got to use 3 decimal places. You can either round or truncate. That means chop off after 3. But if you do not use at least 3 decimal places, you're going to lose the points on any free responses that have that. All right. So we're going to look at the same thing, and we're going to rotate around the line y equals 2. So let's just kind of take a look at what's going on here. So we've got the same kind of weird thing going on. And I like that I made this kind of small. So I'm going to take this bluish region, and we're going to spin it around the line y equals negative 2. So I'm going to use that and spinning around. That's going to make kind of a donut-y type thing. I've got a nice big hole in the center, and that blue region is going to track some kind of a disc around the outside with a big hole. You might call this a washer. So what that really is telling us to do is that we're going to build the shape based on the top curve, and that's going to be my radius for that. And from that I'm going to subtract that bottom curve's shape. The cross sections for these are going to be circles, so a is equal to pi r squared, and we're going to use the same intervals to make this happen. I like doing this as two separate integrals, although you don't have to. And the first integral, this is going to be for the outside part. I'm going to do this as the integral from negative 0.9046 to 0.9530, and that top curve is going to be that exponential thing. That's called f of x, so I'm just going to label this. And I'm just going to label the other one h of x. Just so I don't have to rewrite everything, and that's totally fine for you to write on your spirals as well. So to get the first radius here, because we know that's pi and then radius squared, it's going to be f of x minus, and then this has a height of negative 2, or f of x plus 2. That's going to give us a value that we need, and we can actually kind of put that into the calculator at this point. I'm going to use second entry, so I don't have to rewrite everything. And there are ways to do this on the calculator so that you don't have to deal with typing in the 2 to the 0.25x. If you graph these things, you could put in y1. Now I'm happy to show you how to do that. But I'm going to put in my squared, and I'm going to put in my pi. And when I press enter, we're going to get our value. Might be nice if I actually put the minus 2. Alright, so I've got 2 to the 0.25x plus 1, that's that first graph, minus negative 2. That's all in parentheses squared. I've got a pi in front of it. And when I do that, I get 93.824. Okay. I'm just going to do 236 just in case we get some kind of funny rounding. And then I'm going to do the same thing for the other function. So this is going to be the red function, and this is the radius that we're cutting out. So we were doing the same interval, so negative 0.9046 to 0.9530. And this is going to be h of x minus negative 2 dx. And again, I'm just going to go back to my calculator. I've already got the integral set up, so I'm going to use that same thing, but instead I'm going to use the other equation, which in my calculator is y2. So I'm going to end up typing that in here. We're going to do function under y vars, y2 minus negative 2 squared dx. And when I do that, I've got 12.751, and I think that's because I forgot a pi. So let's go back in because we don't want to lose the pi. And that gets me 40.0585. We're subtracting these two. So we got 93.8236 minus 40.0585 to get 53.7651 is your answer. Just to kind of summarize what we did here, we realized that if we're spinning this, we're talking about circles as a cross-section. That's a equals pi r squared. We know to find the volume, we have to do the integral of some kind of cross-section. We're adding up all these slices, and we're going from the beginning to the end. Because we're doing a weird shape, it's going to be kind of a disc thing, where we have this outer layer in my awesome art skills, and then we're cutting out this middle part. That's how we did the top curve minus what we're rotating to get our first radius. That's the big one. And then the red radius is going to be the bottom curve minus that rotation axis, just so we can get these radii to go into our equation. All right, next up we've got our MinMax FF prime F double prime. This is the second time that we've seen this on a spiral, and each of these is going to be added to your free response score for this section. So we got a couple more of these to do. What I'd really like you to focus on is on trying to make sense of the math that's going on here, and understand that you do have the math to do these, but you have to interpret what's being said, and that's hard. It's not an easy task. Although these questions are not necessarily designed to be tough questions, it's just a matter of the difficulty in understanding what's being asked. For the first one, we're looking for the x-coordinate of each relative minimum on the interval from -2 to 3. So when I look at this, I'm thinking about f prime changing from negative to positive. I know that when f prime changes from negative to positive, that we have relative minima occurring. So I'm going to look at the f prime part of this. Oh man, we got two different equations, or two different functions going on here. So I'm going to look at f prime. We're at -0, then back to negative, then 0, then we're going to positive. And that happens at x equals 1. So at x equals 1, f prime goes from negative to positive. X equals 1 is a minimum value. And hopefully you're not writing with stylus, so you can actually write some of these things out a little bit more comfortably. Part B. Why must there be a value such that f double prime of c is equal to 0? The first thing I notice is that as soon as I see a why must there be a value, I want to think existence theorem. This is going to be an EVT, IVT, MVT question. And there are a couple things that are going on here. The first is that we don't have any information for f double prime. So what we'd have to do is to think about this in terms of the slope of the values that we have for f prime. Since we're talking about a derivative and we have some other things that are part of this, I'm going to think MVT, because MVT tells us that the average rate of change on an interval has to be equal to the derivative somewhere in that interval. We also have f prime is differentiable. It's really important to say that when you're in the world of EVT, IVT, MVT. And looking at this, and by the way, I know that because it says that this is twice differentiable, so that it means f prime is differentiable. F prime of -1 is 0. We've also got f prime of 1 is 0 too. That means a couple things. The first thing it means is that if we've got f prime of 1 minus f prime of -1 over 1 minus -1, which is 0, by MVT, f prime of c must be 0 on the interval -1 to 1. Somewhere between these two values, because we have the same height at both things, by the way, this is also called Rollies Theorem or Rollies Theorem, although that's just a special case of the mean value theorem. The average rate of change on this interval is equal to 0, so somewhere in there we have to have a derivative that's also equal to 0. That's really what we're getting at there. Alright, the function h is defined by this funny thing. I'm going to zoom out so I can write this on the right side of the screen. And when we do that, I want to close this so I can see. You guys can't see the pen thing, but it was getting in the way of me reading this. So we got h of x is equal to ln of f of x. Okay. We want to find h prime of 3. So for part C, h of x is equal to ln of f of x. And we've got to find h prime of 3. So h prime of x would be the derivative of ln of stuff is 1 over that stuff, multiplied by the derivative of that stuff. So h prime of 3 would be 1 over f of 3 times f prime of 3. Okay, looking at my table, that's where I'm going to get this stuff. We have values at 3. F of 3 is going to be 7. So we got 1 over 7. And then f prime of 3 is going to be a half. So we got times a half, and at this point you're done. Part D. We're evaluating an integral from, it looks like -2 to 3. F prime of g of x multiplied by g prime of x. We're really bad at seeing these things as functions that are going on here. But really what's happening is we got a function within a function, and that function on the inside would be g of x, which means that my u in this case was going to be g of x. That means that du dx is g prime of x, and that my dx is going to be du over g prime of x. When I plug that in, what I'd like us to notice is that that's going to cancel this part out on the outside. This is just the derivative of f of g of x. So one of the things that you might notice is that this would end up being, that's a terrible f, of g of x. And you might not even need u substitution to see that. And then we're going to plug in positive 3 and -2 and subtract. So then when we look at this, so this is going to be f of g of 3 minus f of g of -2. And that's going to be g of 3 is 1. So f of 1, g of -2 is -1 minus f of -1. So f of 1 is going to be 2. F of -1 is going to be 8. 2 minus 8 is going to be -6. And finally, we got the new section. This is rate in and rate out problems. And here we got a storm washing away sand from a beach. And it's talking about distance from a road. We've got the distance is going to be this function here. The edge of the water was 35 meters when the storm began. So I'm going to say that f of 0 is equal to 35. That's a starting value. We'll probably need that. They also give us the derivative. We're told that the storm lasts 5 hours. Okay. What was the distance between the road and the edge of the water at the end of the storm? All right, so the first thing that I need to understand is what's going on here. I'm going to zoom in so I can write smaller. We're told that A, is it this one, that f of t is the rate. So what this is really asking is us to find how much it has changed over time. In other words, how much it has accumulated. So you might say that the distance, which starts at 35, and then we got to find the accumulation from time 0, it says the storm lasts 5 hours, to time 5 of f of t dt, which is the square root of t plus cosine of t minus 3 dt. And this is calculator active, so at this point all you got to do is plug the numbers into your calculator and you'll get an answer for that. The one thing that you do have to be really careful about is that you absolutely have to be in radians. If you're in degrees, and we had some issues on spiral 13, where a number of you were in degrees, you will get these questions wrong. The math is not the same. And in order to be in the ballpark of what's going on here, you've got to be in radians. Okay, so while I was talking, I plugged that into my calculator. It's doing the thinking now, and I get negative 8.505. So at the end of the storm, we're looking at 35 minus 8.505. I'm going to add a 3 in there for good measure. Remember, you need 3 decimal places or more if you are in the AP side of the course. And when I do that, we get 26.4947, and that's going to be in meters. You may or may not need to use meters. You'll be told if you have to use units, but it's always a good practice to understand what we're dealing with here. And especially like Part B, it says we have to use the correct units to deal with this. Okay, so that's Part A. Part B is actually not asking you to do some math. It's an interpretation question. The good news is if you have no idea how to do Part A, you don't need that for Part B. Okay, so f prime of 4 is equal to 1.007. And let's think about this in terms of what's going on here. So we know that f of t is a rate, and it's going to be meters per hour. The derivative of this is how fast this is changing. So this would be meters per hour, or meters per hour squared. And it would not be okay to call this acceleration. That's something really specific, but this is kind of like that. So if f is the rate of change of the distance, this would be the rate of change of the rate of change. So it might be how much, maybe let's call this the rate at which the distance is changing. Is changing. That's a really confusing sentence. But we're talking about a double rate here. at time t, at time 4 hours, is 1.007 meters per hour squared, or meters per hour. We could probably write this in a much more concise way based on this value. So this is going to be kind of alternative, a better answer for this, hopefully. At t equals 4 hours, the is it the water or the beach that's getting closer to the road? It's the water that's getting closer to the road. So the rate the water was getting closer was changing at 1.007 meters per hour squared. That's a more precise version of this. There's less double using words to get that reasoning in there, but that will get you where you need to be as well. Okay, for part C. At what point during the 5-hour storm was the distance between the road and edge of the road decreasing most rapidly? Okay, so I'm looking for a rate that is a maximum rate. So I'm looking for when f of t has a maximum or minimum value. In this case, most rapidly, but it's decreasing most rapidly. So this is like minimizing this, because the more negative that f of t is, the better off that we are. So the first thing that I might do is to try to find where f of t is equal to 0 and use that to find some minimum values. Again, I've got my calculator. This is a calculator active question. So we're going to type this in as 1 divided by, I'm going to use parentheses, 2 times the square root of x. I'm going to close my parentheses. And then minus sine of x. Once again, if you're not in radians, you will not be okay for this. Before I even go to my graph and go to my window, I'm going to set this from x equals 0 to x equals 5, since that's the time of the storm. And those are the only zeros that I care about. Okay, we've got a couple of zeros. We've got a 0 pretty early on in this interval that's going from positive to negative. And then we've got a second 0 maybe about halfway in that's going from negative to positive. That's the one that we want. So we're looking at what exactly is happening here. So at the time is equal to 2.8403 hours. F prime changes from negative to positive. Therefore, you like my sort of sideways word? F of t is at its most negative, or I'm going to say at a minimum. And that's the only minimum on this interval. The only other place that we have to check would be any endpoints. So we'd also probably have to find f of 0 and compare that to f of 2.8403. So f of 0, f of 2.8403, 2.8403 are the two things I need to look at. And I'm going to plug those into my original equation. I think I still have that more or less. No, I don't even bother in my calculator. Okay, so I'm going to do square root of x, and then plus cosine of x, close parentheses, minus 3. And I stored that value as x, so f of 2.8403 is going to be negative 2.269. F of 0, I'm going to store 0 as x. We get negative 2, so that second value is our winner. You got to be careful with endpoint things. You may end up having something that you need to deal with. Okay, and then finally, for part D, we're looking at after the storm. So we set a part D down here, and when you look at that machine pumping things, it's going to have this rate of G of P. So we're going to talk about this as the integral from 0, let's call this, I don't know if we want to use x or p. It doesn't really matter that much, but let's call this x so we can keep this G of P, so that's our rate function. And that's got to be equal to what we had at the beginning. And actually that's totally incorrect. We're not equaling that value, because that's the distance from the road to the beach. We want to get back to the original. So this has to undo whatever we did in the first problem, which is this function here. And we've got to undo that 8.5053. If you'd rather write that as an integral, you can go from 0 to 5 of f of t dt. The big idea is that we have to undo the amount of distance that the sand was pulled away, and that's about as simple as you can get for that part.